Hello and welcome to the 11th lesson in this series on metric and topological spaces. In this lesson we're going to be looking at connected spaces, and as always in the description is the booklet to follow along with and for the homework exercises. Okay, so the idea behind a connected space is that we want to understand whether or not a topological space can be split up into two parts. So here we've got two disconnected regions, and very loosely we can cover each of them in open sets, but we see that covering in open sets is disjoint. So those open sets on one part of it don't intersect the open sets of the other. So let's look at how we would define this properly. So if we have a topological space x tau, this space is disconnected if there are non-empty, disjoint open sets A and B, such that X is the union of A and B. And then if not, we call the space connected. Then if we want to look at a subset, and we want to ask if a subset or a subspace is connected, then we could either use the subspace topology, or as an equivalent definition, so a subset is called disconnected if there exists non-empty disjoint open sets A and B such that the intersection A intersect Y and B intersect Y are both non-empty. So that's equivalent to the non-empty part above. And Y is covered by A union B. And if this isn't the case, then we call the subset connected. Okay, we're now going to prove that R is connected. Now intuitively, we know that if we try and cover R with a load of open intervals, then all those open intervals will have to overlap somehow. However, actually proving this is quite involved. And unlike a lot of proofs we're going to see in this lesson, it's going to be a proof by contradiction. So we're going to start by assuming that R is disconnected. Then, because it's disconnected, there are two non-empty open sets, U and V, such that the union of U and V is R, and the intersection of U and V is the empty set. So U and V are disjoint. And note that this implies that V is the complement of U, and vice versa. Okay, now without loss of generality, assume that there is an A in U and a B in V such that A is less than B. Now if this isn't true, we can just switch U and V around, so therefore it doesn't matter which one we picked. If it doesn't hold for one of them, then we can just use the other one. Nothing will depend on the order, so that's why it's without loss of generality. Now we let A be the subset of all points in U that are less than B. Then let C be the supremum of A, so that's the the smallest upper bound. And recall that if we say have an open interval, then the supremum of 0, 1 is 1. It wouldn't be something like 0.999. Okay. Now assume that C is in U. This means because U is open, around that point C we can create a little interval. So there exists an epsilon such that C minus epsilon, C plus epsilon is contained within U. And we make it so that C plus epsilon is less than B. So this interval is not only contained within U, it's also fully, everything in it is less than B. But this is a contradiction. Since we've said C is the greatest value in U that is less than B, the existence of this interval that is in U and the upper bound is less than B contradicts the fact that C should be the greatest possible upper bound. And therefore, C cannot be in U. Similarly, let's assume C is in V. Again, V is open, so there exists an epsilon such that C minus epsilon to C plus epsilon is fully contained in V. But this is a contradiction, as the supremum of A must be less than C minus epsilon. As if it were not the case, then this interval would not be fully contained in V. Therefore, the point C is not in the set V either. Therefore, the union of U and V cannot be all of R. There's a point missing, that is the point C. Therefore, we've reached our contradiction and R must be connected. Okay, that was very involved, particularly the 2 points underneath, assuming C is in U and assuming C is in V. So I'd recommend going through and reading this all again and really trying to work through it. If it's really difficult, all of the notes provided in the booklet will have kind of a different explanation of this that might be clearer. Okay, for the next example, I'm going to say, show that the subset 0, 1 is connected. Now the proof here is almost exactly the same, so you can follow it through and make any of the necessary adjustments you need to. Although, considering this is quite difficult, it might be worth leaving until the end of the video when you've had a bit more time to practice and really understand these points. The examples from here on do get easier. So for the first one, consider R with the standard topology. Show that the subset 0, 1 union 2, 3 is disconnected. So to show that, we want to find 2 open sets in R that intersect the subset here and are mutually disjoint. So an example here are the 2 intervals given here. Note that these are open, they are disjoint, and they cover the subset. Okay, for the next example, we want to show that the subset Q, so that is the subset of rational numbers, is a disconnected set. So on your own, have a think, and then come back to the video. Okay, now you've had a think, I'll go through the solution. I mean, this is a solution, there's lots of different possible ways of doing this. But one example is to consider these 2 intervals. These are open, they're disjoint, and they cover the rationals. And in fact, they almost cover the reals. The only point missing is root 2. And obviously root 2 is not rational. Okay, for our next example, take any set X with at least 2 elements and with the discrete topology. Show that this set is disconnected. So have a think and then come back to the video. Okay, now you've had a think. So recall that with the discrete topology, every set, every single point is open and therefore must be closed as well. Now just take any point in X. Then the 2 sets, A and the complement of A, are open and disjoint, and because there's at least 2 elements, both of these are non-empty, and therefore X must be disconnected. Now for the next example, take any set with the indiscrete topology, show that this is connected. Okay, have a think and then come back to the video. All right, now you've had a think. This follows quite quickly from the fact that the only non-empty open set is X itself. And recall that to show something is disconnected, we needed two different open sets, but here there's only one. So it cannot be disconnected and therefore it must be connected. Our next example is a theorem. So prove that X tau is disconnected if and only if there exists a continuous surjective map, F maps X to 0, 1, where 0, 1 has the discrete topology. So because this is if and only if, we need to do it in both directions. I will go through the first direction, and then you go through the second, and then I'll go through it after. So let's start by assuming that X tau is disconnected. Because it's disconnected, there exist two open sets, U and V, that are non-empty, open, they're disjoint, and the union of them is X. Then we define the map as F on U is 0 and F of V, or any point in V, is 1. F is continuous as required. So if we take the inverse of 0, which is an open set, that gets us U, which is open. Take the inverse of 1, that gets us V, which is open. So it is continuous. We still need to check its surjective. And it is because U and V are both non-empty. Therefore, there is any element in U will go to 0, any element in V will go to 1. So it does cover the set 0, 1. Now, on your own, do the reverse direction and then come back to the video. Okay, now you've had a go. I'll quickly go through the proof. So we take U and V to be the pre-image of 0 and 1. These are disjoint because 0 and 1 are disjoint. F is surjective, so both U and V must be non-empty. And they're open as F is continuous. Therefore, X must be disconnected. Then, a corollary from this, X is connected if and only if the continuous maps from X to 0, 1 are constant. So in other words, it's not surjective. Everything would get mapped to 0 or everything would get mapped to 1. Okay, we have another theorem. That is, if X and Y be topological spaces, and F is a map from X to Y that is continuous, and if A is a connected subset of X, then F of A is also connected. The proof for this is in your booklet, so take some time and read through that proof, and then we'll see a couple of quick implications of this theorem. Okay, now you've read through the proof, we've got a couple of corollaries. Firstly, this means that if X is connected and F is surjective, then Y is connected. And similarly, if X and Y are homeomorphic, then X is connected if and only if Y is connected. A different but related notion of connectedness is something called path connectedness. So here again, we've got our disconnected space. And if we take any 2 points in one of the connected regions, we can draw a path that goes from one to the other. However, if we try and draw a path that goes to this point in the other region, it can't be done. It has to leave the space somehow. Okay, now let's formalize this. So, a topological space, X tau, is path connected if, for any pair of points, U and V, there exists a continuous function gamma from the interval 0, 1 to X, such that gamma 0 is U and gamma of 1 is V. And we call the gamma the path. So in general, a path is a continuous function from 0, 1 to a space. Now, if we want to look at a subset, and ask if that's path connected, we could again use the subspace topology. Or an equivalent definition is a subset is path connected if any pair of points u and v in that subset there is a continuous function gamma from 0, 1 to y, such that gamma of 0 is u and gamma of 1 is v. Now that's almost exactly the same. The key difference is that the path is 2y. So the point is the path never leaves the subset. Okay, for our next example, or our first example, with path connectedness, consider the space R squared with the standard topology. Show that this is path connected. So let's take any 2 points and we can explicitly construct a path between them. And then this path here is continuous. And when lambda equals 0, we're at x1, y1. And when lambda equals 1, we're at x2, y2. So we just prove this by explicitly constructing the path. Okay, for our next example, show that the subset 0, 1 union 2, 3 is not path connected. This is actually maybe a little bit trickier than it first appears. So I'm going to give you an informal proof or a formal proof, depending whether or not you've seen real analysis. The informal one captures all the ideas, but the formal one really proves it rigorously. So informally, we can construct a path. This path starts in the first set, ends in the second, as we can see. But however, at some point it does leave the subset. So 1 point, if we sub in lambda equals 0.5, then we get 1.5, which isn't in the set we care about. And maybe you can see that we kind of expect this to happen because there's that gap there. More formally, you'll need real analysis for. So recall that the intermediate value theorem says that for any continuous function where f of a is not equal to f of b, then for any v between them, there exists a little v between a and b, such that f of little v equals big V. Which is basically just saying that we take any point between f of a and f of b, any function that goes from one to the other will cross every value in between. Therefore, any continuous function with f of 0 in 0, 1 and f of 1 in 2, 3 will have to pass through every point in the interval 1, 2. Okay, for our next theorem, let x and y be topological spaces, and let f maps x to y be continuous. Then if a is a path-connected subset of x, then f of a is path-connected. All right, have a read through the proof, and then come back and I'll go through a couple of corollaries. Okay, our first corollary is that, therefore, if x is path-connected and if f is surjective, then y is also path-connected. And secondly, if x and y are homeomorphic, then x is path-connected if and only if y is path-connected. Okay, our next theorem is that if x is path-connected, then x is connected. So in other words, path-connectedness is a stronger notion than just connectedness. And you can kind of see why here. This space isn't connected, and so you can't draw a path from one point to another. Now the proof for this is in the booklet, so read through it. But at this point you might be thinking that, is this true in both directions? So if x is connected, then is x necessarily path connected? And we'll see in the next slide that this is not necessarily true. Okay, our counterexample is called the topologist's sine curve. And this will show that we can have a set that is connected but not path connected. So in red, we have the sine curve bit, so that's y equals sine of 1 over x. And then the blue dot is just the point 0, 0. Now, the red bit alone is path connected, right? I mean, it's basically a path as it is. So it's quite easy to make a path from any 2 points in it. However, if we include 0, 0, it's not, the whole set is not path connected. We can't make any path starting at 0, 0 that goes to anywhere else. However, any open set containing 0, 0 intersects the sine curve. So there's an example of an open ball. B epsilon 0, 0 will intersect this sine curve. And therefore, this whole set is actually connected. We cannot create an open set that just contains 0, 0 and that is disjoint from the rest of it.